speaker. The Professor Arindam Ghosh from IIT Bangalore, and he is quite well known in nanoscience in India. So he didn't need much introduction, but just to carry forward our colloquium tradition and for the sake of our student, I would like to add few words about him. That he completed his MS and PhD from IIT Bangalore in 2000, and then and subsequently he went for postdoc in Cavendish Laboratory in Cambridge University, and he stayed there until 2005. And in that same year, he joined IIT Bangalore as an assistant professor. So since then, he has been contributing a lot in nanoscience in India. His research interest mainly lies in the structural, electronic, and magnetic behavior of nanomaterials, and he works in many fields that you can get by going through his website. He has several patents from his lab in ISC, and at present he is also associated with Nanoscience and Nanoengineering Department of the IIT Bangalore, Center of IIT Bangalore. And there are many awards that he has received due to his quite active contributions since couple of decades in nanoscience, and few of them like Swarn Jayanti Fellowship in 2009, 2012 he got Santi Swarup Bhatnagar Award, 2015 he got Young Scientist of India. He is also fellow of Indian Academy of Science and National Academy of Science. And since last couple of years, he is quite actively working on 2D nanomaterials, especially twisted bilayer graphene. And today he'll be saying much about that how the engineering can play a very important role in bringing some beautiful effect out of these two-dimensional bilayers. So with this, I would like to invite him for today's colloquium on engineering the flow of charge, light, and heat with atomic layers. And I hand over the forum to the Professor Arindam Ghosh. And before that, I would also like to thank Saurabh Basu for coming with this idea to invite, let's invite Arindam, although he will be quite busy, but let's try and get him on the board just for sake of our students. And he also shared many interesting stories since his undergraduate days with him. So just before starting, I would like Saurabh Basu to say a few interesting things about Arindam.
Oh, thank you. I mean, you don't have to thank me, Pankaj. So just for the audience, he's an excellent cricket player. So much so that he played first class in Bengal, first class cricket in Bengal when he was in his college, and then went on to play county cricket when he was in Cambridge. So, and in his own words, he has done more cricket than postdoc, which of course we don't believe, but I believe that he has done both and equally well. So over to you, Arindam, and thanks for joining us. Thank you.
Oh, you're welcome. Okay, I mean, let me just first, all right, I hope you can see, just let me know if you can see it, right? Pankaj?
Yes, we can see it, slide. Yes.
Yeah.
Good. Okay, good. First, thanks, Pankaj, for the introduction, Saurabh, for letting the secrets out. Yeah, I mean, we used to do both, both during my PhD days at IISc and outside, and even as a faculty. So it's always very nice. Okay, good. First of all, it's a pleasure to talk to IIT Guwahati crowd again. I have been getting there off and on, but it's always good to spend time. And hopefully in the near future, when all these virus thing goes away, we should be meeting again. I'm going to talk a little bit about what we have been doing in light matter interaction and how to engineer new devices with atomic layers. I'm sure many of these are known to you because these are very in field of research. So let's get ahead with it. I mean, I'm quite sure graphite is something which is not unknown to anybody. I was told that, I would like to start with a little basic level, but then we will graduate to more cutting edge research. So hopefully there is a take-home message for everybody out there. Okay. So graphene has, created a lot of interesting possibilities. And we now have device paradigms that's coming up, because from now the European Union is extremely excited in application of graphene, from flexible electronics, papers, and to strain engineered materials and so on and so forth. What is the number of papers, since this is slightly older statistics, now it's thousands, tens of thousands per year on graphene alone. Now, from there are about more than 200 companies on this topic that they're all over the world. So you can imagine how heavily this field has developed over the last decade and a half or so, 2004 to 2020 today. It's expected about $1.5 billion market just on graphene in the next 2 or 3 years, or maybe 4. So yeah, I mean, all these things really started when we recognized, or this was recognized much earlier, that graphene belongs to this class of compounds, which is called layered solids, where the layers are strongly bound in plane, but they are not so strongly bound out of plane. For example, you can see the van der Waals force between two layers in graphene is about 100 to 1,000 times less than a standard three-dimensional covalent bonding or ionic bonding. Okay. So that made the whole field start when you could exfoliate those materials, and it's huge. Now the family of these materials is, in principle, what can be exfoliated, and look at the numbers here. So if you have typical binding energy between two layers, approximately in the order of 10 to 20 millielectron volt per square angstrom, it's easy to exfoliate. That means you take two tapes and you just cleave the material and it will form nice layers. Okay, nice along a lattice plane, you can exfoliate them. There could be about 1825 according to calculations now. So imagine the phase space, of which we know probably about 30 to 35 can be separated in terms of exfoliation and stabilized and made devices of today. And this number is increasing. Okay, and these numbers are staggering, because even with one, like graphene, the number of properties we can get is massive. And I'm going to show you a little bit of that. Okay, so this whole concept of exfoliation is the reason why we could get this system of these layers on a substrate. Okay, usually these substrates are silicon oxide substrates, and once those substrates are created and you use a Scotch tape to stabilize, and this is a very well-known technique now, one can actually make devices by putting contacts, okay, electrical contacts. And this is how a typical device look like. Now, once you have a device like that, you can make a field effect transistor. So original graphene paper actually was demonstration of a field effect device, in which you use the heavily doped silicon and apply potential voltage on that, in which the silicon dioxide layer acts as a dielectric. So the graphene layer on top acts as is capacitively coupled to the gate, and you can change the electron density or the hole density. So if you make the gate voltage positive, you induce electrons, and if you make the gate voltage negative, you induce holes. And in both cases, the electron or the hole density, the charge density goes up and the resistance comes down. So that's the field effect device that one is talking about. Excuse me. Now let us go a little bit more detail about the band structure of graphene. And this is why I wanted to say that, the 1825 materials that are potentially possible, even graphene alone, one, is exceptionally interesting from a number of point of view, and I'm going to show you that. Okay, so this is hopefully some people who are trying to understand what they would like to do in this field, hopefully you will get some ideas. So, for example, if you have a band structure of graphene, which essentially means that, which is a hexagonal crystal lattice, and if you take the Brillouin zone, which is also hexagonal, and you simply take a tight binding model, and you will be able to solve that to get a band structure that you can see over here. Let me just try to see if I can. Yeah, okay. So you can see that these, I don't know whether you can see my cursor, but anyway, hopefully you can. So if you see these points where the conduction band and valence band touch, they are what you call the Dirac points. And around the Dirac point, you have this conical band structure, which is why the dispersion relation at low energies is linear, and graphene electrons behave as light, although at much lower velocity, which is about 10 to the power of 6 meter per second, you get a linear dispersion. Okay, right. So that's the case of infinite graphene, and this is where the interesting thing starts. What about the semi-infinite graphene? And the semi-infinite graphene means that you will have two edges. So this is a square. So you have, if you see this edge, which is on the left. By the way, can someone tell me whether they can see my cursor, or I have to do?
Yeah, we can see your cursor.
Okay, good. So if you see this, my cursor, this is called a zigzag edge, and when you see this bottom one, it's called a armchair edge. Okay, because of the topology of the carbon atoms. Again, if you simply do a standard tight binding theory, tight binding model calculation, it's very easy. We just have to take the densities from each or every atoms and then just simply add it up with appropriate boundary condition and the condition of orthogonality. Okay, then you will see something really interesting about these two edges behave very differently. So for example, if you have an armchair edge, you will get a gap structure, which is at 0K, there is a gap. Whereas if you have armchair edge, this is zigzag edge. In the zigzag edge, you get a completely different behavior, which is there is a zero energy state. Okay? So there is one particular band which essentially becomes zero energy, and this is something which very similar to what happens in topological systems. But this is not topologically protected, because if you create lattice defects, then these zero energy states go away. Now, we were one of the first set of people to actually show that zero energy states could host dissipation-less current, even at very high temperatures, at room temperature. So you can see the conductance of these zero energy states can actually be E squared by H, which essentially is the quantum of conductance, which is like a one-dimensional conductance state. This quantization was observed at room temperature. So this is where you can use graphene edges for making circuits, which can do.
Arindam, just
sure.
Is there armchair? There's no restriction on the number of unit cells for it not to have a zero mode.
The zigzag, you mean to say, the armchair will never have zero mode. The zigzag will have zero mode, but
the armchair also depending on certain length, wouldn't have also it have a zero mode?
No, as far as I know, by finite length of the armchair.
Finite length. I think there's some restriction on the length, which is some 4n plus 1 into some a by 2.
Right. So we have taken very large n here. Okay. So at a very large n limit, you don't get a zero mode. And so this is something which you need to check. As far as I understand, this is done on 96n or something of that sort.
Okay.
Excuse me. But in the case of zigzag mode, even if you have got a very large n, but you have got width to be small, then these zero energy states go away. So you can open a gap at zigzag as well by finite width of the ribbons. Okay.
Yeah.
So anyway, so we have been working. I don't want to talk about too much on this because today's agenda is different. Okay. Then bilayer graphene is very interesting as well, because here you have got 4 electrons in a single unit cell, 2 from each layer. And that leads to, in the low energy band, spinner type with layer 1 and layer 2 acts as the spinner, okay, like an equivalent spin. Okay, so this is because of the interaction between the layers. You don't have the linear band structure anymore, but you have parabolic band structure, but with a spin-up. And that leads to something very interesting, to marginal topological insulator properties. I'll just give you a very brief look how it looks. For example, this have this, you take two layers of graphene, but they are decoupled from each other. Each has a conical band structure, but then you apply an electric field on it, say for example, and then you shift them because you create a voltage difference between the two. And then you turn